All right, everybody, we have at this point identified the key considerations for running these single sample t-tests compared to the z-test we previously ran. So now we're going to walk through an example of that and see what this test looks like in practice and how we account for these different calculations, different kinds of information. So we'll start by reviewing the steps and then we will get into our specific example. So again, step one hasn't changed. It's still identifying an alternative and a null hypothesis. The alternative is generally what the researcher expects to happen. The null hypothesis is whatever possibilities are left over. And again, we have two populations. Population 1 is going to be the one represented by our sample. Population 2 is our basis of comparison, sort of our control group, even though we don't have a control group in our samples yet. Step 2, we're still providing the same three pieces of information, the mean, the standard error, and the shape, but two of those three factors are changing. First, we no longer know the population variance or standard deviation. We have to calculate it from our sample data by calculating our sample variance. Again, we are using the version of those formulas with n-1 in the denominator, which itself refers to a concept called degrees of freedom that are going to matter a couple of times here. So we use that n-1 denominator. By the way, on exams and stuff, that's going to be the only information you have. Don't worry about picking the right formula. You're only going to have the n-1 version. So if their sample size is larger than 1, which it always is going to be from here on out, we will also convert that standard deviation to a standard error. But the key difference there is we need to estimate it from our sample data. It's not information we already have. The shape of the comparison distribution is no longer normal. We need to say two things about it now. We need to say it's a t-distribution, and we need to identify those degrees of freedom. That simply is the number of people that you measured minus 1. It's already the denominator over here. So it's something that you'll already have calculated, but it's something you have to remember to do, and also to explicitly flag it as the t-distribution. The population mean, either you'll have it or it'll be very easy to estimate due to basic things like the chance standard of guessing. Then we find the threshold or critical value, or values if it's two-tailed. Again, we can use the t-table for that. You'll have to do that in some of your practice examples, but it's not a necessary skill for the exam. Step 4 has changed very slightly. The t statistic looks very similar to the z statistic for sample means. The only difference there is that we now have the sample standard error here being used to estimate the population standard error. But it's a deviation score on top, standardized by dividing by standard errors. It tells you how many standard errors apart your sample mean and population mean are. Step 5, we compare step 4's result, that test statistic, to the thresholds from step 3, and we make a decision about the null. If the test statistic is beyond the threshold, if it's farther from the mean than that threshold or that critical value, we reject the null. If not, we fail to reject the null. All right, let's look at an example hypothesis test. So before we get started on this, what I want to tell you is that what I've done on the board here is something that I recommend that folks do, especially the first few times through these sort of problems. Make just a list before you even worry about the steps or anything. Make just a list of key information that you're going to need about each hypothesis test, and then kind of pluck that information out as you get it. So here I have some basic stuff like the alpha level, the number of tails, the number of people, degrees of freedom. Then I have some descriptive stats over here, the population mean, the standard error that we'll have to calculate, and the sample mean. So these are seven pieces of information that I'm going to want to pull out before I even worry about anything. So here's our premise. Let's say that it's a decade from now and you're all working as professional statisticians, and somebody comes into your office and says, I'm looking for a statistical test. And you say, oh, what are you looking for testing? He says, well, I'm a professional dog sexer. And you say, whoa. And he says, well, hang on. That's basically what we do is we assess the perceived sex or gender of a dog based on looking at a picture of them. And you say, well, that seems like a pretty limited business model, and there's got to be a better way of explaining that, but we can test that. He says, okay, I have 5 employees, and what I want is a little bit of evidence to support the idea that they're really good at identifying the gender of a dog by looking at its picture. So we say, okay, we can test that. That's a little weird, but that's something we can assess. We'll use a standard two-tailed test with an alpha of 0.05. So we have a couple of key pieces of information already. Alpha is 0.05, sorry for my sloppy handwriting, and it is a two-tailed test. By the way, this example will be supplemented by pictures of my dog. So that's my dog down there, and the dog's name is Ollie, and he is a very good boy. So if you guessed boy dog, you are perhaps a little better than the employees of this business. Perhaps you could get a job there. So here's another piece of information. We say, okay, what we want is that we want to know if these people are better or worse than chance. We want to know if they differ from a chance standard. So what's a chance standard? Well, we know that about half of dogs are boy dogs, half of dogs are girl dogs. And so we know that if somebody just guessed at random, we would expect them on average to get about 50% of those guesses right. That is our population mean. That's going to represent the mean of population 2. Notice that that wasn't spelled out in the description. We figured it out pretty easily based on just basic probability. If half of dogs are male, half are female, then the mean for correct answers would be about 50% if you were just guessing. That's our chance standard, and we want to see if our employees differ from that. So, for simplicity's sake, we'll just write that as a whole number, 50. Now, let's look at how we would structure this test. Here again is Ollie being taunted by charcuterie. And what we would be doing to construct a test here is first building hypotheses, but before that identifying what populations we're comparing. Population 1 is the one represented by our sample. Those are people like our employees, people that pick a sex of a dog by looking at their face. So again, it's the population represented by our sample. It's not just the 5 people we're looking at. Population 2 is our basis of comparison. We could call that a chance standard. We could call that people that pick the sex of a dog by chance. There are lots of different ways you could correctly phrase it. Don't worry about getting the exact phrasing right. You just need to express that same idea that this is our chance standard. This is people that don't have any ability to pick or identify the sex of a dog. So our null hypothesis, because this is a two-tailed test, is pretty straightforward. It is that mu1 is equal to mu2. Population 1 doesn't differ from chance. Now notice I plugged in the specific number here, the percentage here. You can do that. You can write mu2. Both are equally acceptable. The alternative is, again, what the researcher is probably looking to assess, and it's just what the possibilities that are left over does differ from chance. We express that generically as mu1 does not equal 50%. So that's step 1. Here's Bat Dog over here, leading us into step 2. And here's where we start picking out some key pieces of information as well. Here are our individual scores. This is what we would start with in a data set. This is the percentage of responses that our 5 employees got right. From that, we can pick out some key pieces of information. We already know the n is 5. And because the degrees of freedom is just n minus 1, we know that that is 4. Going to have to calculate the standard error, the sample mean, which was gotten just by adding all those x's up and dividing by 5. They got 50.6% of their answers right. So that is our sample mean. Well, that's above average, but gosh, it doesn't seem like by much. Let's see how it holds up when we run a hypothesis test. So the last important piece, missing piece of information, again, is the standard deviation, which we will turn into a standard error. So to begin that process, we'll calculate a variance, then we will boil it down until we have a standard error. I'm using the computational formula here that just requires two columns of information. Again, all the individual scores here added up. That's our sigma x. Then we square each one of them. We add those up. That's our sigma x squared. Now, I'm not going to go step by step through this formula anymore. Review module 4 if you're having trouble with it. But sigma x goes over here on the right side of the numerator and is squared. Sigma x squared, the score is squared, then added up, goes here on the left side. And again, after doing some divisions, you wind up with 17.2 as your sum of squares. That's your numerator. Remember, sum of squares is going to be real important later on. 4 is our degrees of freedom, our n minus 1. When we divide, we get a variance for the sample of 4.3. That's our estimate of our population variance. We're not done yet. We turn it into a standard deviation by taking the square root. After rounding, that's 2.07. And we convert that to a standard error by dividing the standard deviation by the square root of the number of people, 5. We wind up with a standard error of 0.92. So, at the end of step 2, what we would wind up with is those 3 pieces of information. It's a t-distribution with 4 degrees of freedom. That is, again, our shape information. The comparison distribution has a population mean of 50%. That's our chance standard, and we just determined that the standard error is estimated to be 0.92. Here's Ollie chilling with a beer on the lawn, waiting for you to figure out how to finish it up so you can go hang out with him. So, step 3, again, you can use your t-table to figure this out, but the key pieces of information, alpha is 0.05, it's a two-tailed test, and we have 4 degrees of freedom. If you look at the appropriate row and column, what you will find is 2.776. Because this is a two-tailed test, we need 2 critical values, but because it's a symmetrical distribution, it's just plus and minus the same number. We'll reject the null if the sample score is lower than negative 2.776 or higher than plus 2.776. Basically, scores that are at least that many standard errors away from the population mean have less than a 5% chance of happening as a fluke in that specific t-distribution. So again, we're going to reject the null if we see scores beyond that threshold in either direction. We're going to fail to reject or retain it if it's in between. Now let's calculate our t-score, which again looks an awful lot like a z formula. We have a sample mean, we have a population mean. When we subtract, we find that this sample was 0.6% above the chance standard. So that's their deviation score. We give it context by dividing by the standard error, which is 0.92. What we wind up with is a t-score of 0.65. That means that our sample is 0.65 standard errors above the population mean. One last step. By the way, Ollie says go Celtics. Time is coming. We decide whether or not to reject the null. We compare that 0.65 to our thresholds. I'm going to do something unusual and backtrack here. Remember, we needed a score that was beyond these lines, and the score we actually got was more like here, very much smack in the middle of that do not reject the null area. So we fail to reject or accept the null hypothesis, and that just means the study is inconclusive. We have no evidence that people like the ones in our sample are any better at guessing the sex of a dog by looking at its picture than you would expect just due to pure chance. There's no indication that they're any different from just a pure chance standard. So that's the end of this example. There will be more in the book and the homework and the practice quiz that will be coming up at the end of the module. So if you're confused about this process, you might jump to those and do a couple practice problems. But when you're ready, come back and we will wrap up the module by talking about the concept of confidence intervals.